Thanks to the conveners, and thanks to all of you for staying so long on a Friday afternoon. So we've heard some great talks about how processes in planetary interiors can contribute to habitability, and I'm going to be talking about moments when solid Earth processes can actually render Earth less habitable. So I'm going to be talking about large igneous provinces and mass extinctions. My aim is to summarize where we are in terms of our understanding of the environmental consequences of large igneous provinces, with a particular emphasis on the Siberian traps. So I put up a definition of a large igneous province here. It's a region of extraordinarily voluminous magmatism, lasting several million years or less, and distinct from normal seafloor spreading. Here I've tried to distill the most recent uranium-led geochronologic data from 3 large igneous provinces, the Siberian traps, Camp, and the Deccan traps, and 3 mass extinctions, the end Permian, the end Triassic, and the end Cretaceous. And there's a lot of information on this figure, but the main thing that I want you to take away is that as the geochronologic data has accumulated, the evidence continues to suggest that a number of large igneous provinces overlap in time with major mass extinctions. So are we done? Can we conclude that large igneous provinces cause mass extinctions? Well, I think it's worthwhile to be really cautious about concluding that for a few reasons. First, there are a number of other large igneous provinces that do not seem to coincide with mass extinctions. So these are the guys in black here on this figure. And secondly, if there is a causal link, we do not understand how that link might operate. And thirdly, there is such a thing as coincidence, right? So 2 things can overlap in time without necessarily being causally related. So how do we test this hypothesis of causality? And ideally, how do we investigate the nature of any causal link? So the first step, really a critical step, I think, is the geochronology, to pin down with the maximum possible precision the relative timing of the eruptions and the extinction. But I think that's just a first step. So what can we do next? I suggest that a good next step would be to try to quantify the environmental stresses that might result from magmatism. So, for example, the patterns and severity of acid rain and ozone depletion that might occur following magmatism, and then finally to compare those predictions with what we know from the geologic record about the extinction. So, do those predictions that we can make about specific stresses have explanatory power for what went extinct and where? So I already talked briefly about the geochronology, and for the rest of the talk, I'm really going to be focusing on this second step. What are the environmental stresses associated with magmatism, and how do we get at those? So the approach that I'm going to be following in this talk is really first to try to quantify the overall volatile budget. So what is the overall quantity of gases that might be released? And we'll quantify that with the help of blebs of trapped magma known as melt inclusions. And then can we translate that into a gas flux through time? That's probably the most tricky and uncertain step. And then finally, what are the resulting environmental stresses? How can we map them out into an ancient world? And in my case, I'll do that using a global model of climate and chemistry. So here I've compiled the measurements of sulfur, chlorine, and fluorine primarily from melt inclusions and primarily from extrusive rocks from different LIPs. And so these are the different LIPs here on the x-axis, and then concentration on the y-axis, sulfur, chlorine, fluorine, and those different colors. And my point here is that actually we are beginning to understand reasonably well the overall volatile budget for many of these different large igneous provinces, which is critical, right? Because the gases that are released during magmatism are really the key determinant of the environmental changes that might result. But there are a few things that are missing from this figure. So in particular, the CO2 is not on there, and the production of other metamorphic gases when when intrusive rocks inject into the sedimentary rocks and heat them. And finally, the time-dependent fluxes are not in there. So how do we get at those? We can focus on individual eruptive pulses. That's one strategy to try and get towards a flux with time, because they're slightly better constrained. And then the other strategy there is to look at a range of scenarios. For the metamorphic gases, we can rely on published thermal modeling. And then for the CO2, remember that the CO2 that we might measure in a melt inclusion is probably only a small fraction of the total carbon dioxide budget for the large igneous province. So there are a few potential approaches there. One would be to rely on thermal modeling. Another would be to approach it from the perspective of mantle geochemistry, or else from the perspective of inverse modeling. So these are results from Ying Cui, who's actually inverted the carbon isotopic record at Meishan to try and get at the injection of carbon that would be required to produce that isotopic record, assuming a particular isotopic composition of the emissions. So this is with negative 25 per mil emissions. And on the x-axis, this is for the end Permian mass extinction, I should say, 252 million years ago, right? And so this is, x-axis is time relative to the mass extinction here. And on the y-axis is atmospheric CO2 in ppm. And I'll just point out that you briefly reach PCO2 of around 11,000 ppm, so something like 20 times what we have in the present day. So really extreme. Right? Okay, so what are the stresses that we want to be able to quantify? First, we'd like to be able to get at acid rain and acid deposition and cooling from sulfur on timescales of years. We'd like to be able to get at ozone depletion from halogens also on timescales of years. And we'd like to be able to get at global warming and acidification from carbon on millennial timescales. And we can actually make quantitative predictions, as I'll show you, for all of these stresses. And my approach to showing you the kinds of predictions that we make will be just to give you some snapshots, some illustrative examples of each of these from out of the larger number of model runs that I've done and that other people have done. Okay, so starting with acid deposition and acid rain, I'm showing you results from a simulation that we've done where I put 2,000 teragrams of SO2 into the end Permian stratosphere. And so this is where the Siberian traps are located. And you have Pangaea assembled here from equator to pole. So it's a very different world in the end Permian, right? And the colors just show you how the flux of acid deposition, so rather the cumulative acid deposition during this year that I let the eruption happen, right? So a couple of things to notice. First, the pattern of acid deposition is really distinctive. Particularly concentrated in the northern hemisphere because the Siberian traps are located at high northern latitudes. Second, that's a lot of sulfur. So we can actually calculate the pH of the rainfall that would result from the combination of sulfur and high CO2 levels in this end Permian atmosphere. And the pH would be approximately 2 in most of the northern hemisphere right at this moment. So compare that to squeezing undiluted lemon juice across much of the northern hemisphere, right? Okay, so here I'm showing you a simulation in which we look at prolonged emissions of again, so this is less sulfur, 200 teragrams per year of sulfur dioxide, but put into the atmosphere, the stratosphere, continuously for 100 years. Okay? And these are the annually averaged temperature anomalies across the final 50 years of that simulation. So again, there's a pretty distinctive spatial pattern. Most of the cooling occurs in the northern hemisphere, but the color scale is down here. So we go down to annually average cooling of -2 to -2.5 degrees Kelvin in this case. So that's pretty modest. That's hardly a volcanic winter. So that's consistent actually with some work that Anja Schmidt is also doing on the Deccan traps. Here's a simulation where I look at the effects of more than 1,000 teragrams per year of methyl chloride released into the base of the troposphere. So this is to examine what might happen if you had metamorphic emissions of organohalogens from heating of sedimentary rocks. And I don't think I mentioned, but think of these all of these figures as maps, right, of the end Permian world. So I've just outlined Pangaea here. So the colors are the degree of ozone depletion and correspondingly the increase in ultraviolet radiation at the Earth's surface. So the red is where you have the most ozone depletion and also the largest increases in biologically effective ultraviolet. And the point here is that, again, you have this distinctive spatial pattern, right? Most ozone depletion occurs at high latitudes, both in the northern and southern hemisphere, and it's different from the pattern of the acid rain and acid deposition, which is happening in the northern hemisphere here, right? So that's the first thing to notice, and then the second thing to notice is that you can have quite a lot of ozone depletion. So just for comparison, basically everywhere in this particular simulation, you get down to ozone levels that are comparable to or below the worst of the ozone hole that occurred over Antarctica in the recent past. Here's a simulation where I look at an end Permian CO2 ultra greenhouse. So this is motivated in part by the delta 18 oxygen isotope proxy records and conodonts from across the Permo-Triassic boundary, and also by the inverse modeling that Ying has done. And the colors show from 10 degrees C in black near the poles up to about 50 degrees C in these mid-latitude regions. And this is annually averaged surface temperatures, right? So just for comparison, I don't know if anyone knows what the hottest temperatures on Earth are in the present day, but I think the hottest inhabited place is in northern Ethiopia, and the annually average surface temperature there is around 35 degrees C. So in many places in this ultra-greenhouse world, both in the surface ocean and on land, you might be reaching near lethal or lethal temperatures. But in contrast, at high latitudes and deeper in the ocean, temperatures are less extreme. Okay, finally, I'm showing again some work that Ying has done where she's tried to quantify the response of ocean chemistry to some of these very high, potentially very high CO2 levels. And the top figure, the top panel is with 2,800 ppm CO2, which is already pretty high by any standard. But this is with almost 11,000 ppm CO2. And the colors show the saturation state with respect to calcite of the surface ocean. So here you have, it's basically, if this number gets quite low, then it becomes very difficult for calcifying organisms to actually produce that calcite. And that's the case for most of the surface oceans if you have such high CO2 levels. So just to summarize, we can make some quantitative predictions for the acid rain, the modest the modest cooling and the ozone depletion that might occur potentially in pulses, repeated pulses, but on timescales of years during and after some of these magmatic events, and also for the warming and acidification that might occur on longer timescales. And I think the interesting thing, one interesting thing at least to notice, is that none of these are truly global stresses, right? Some of them are more intense in the ocean, some of them are more intense on land, some of them are most intense at particular latitudes. So I think that's actually a really powerful result in that we can make specific predictions that hopefully we can then test against the geologic record. So how do these predictions compare with the fossil record? I don't actually think I have time to go into the details of, for example, what we know about end-Permian paleontology, but I just want to quickly touch on some of the challenges here and also the hope. So the challenges are, first, the temporal resolution of the fossil record is coarse relative to the timescales over which some of these stresses are occurring, right? The stresses might last only years in some cases. Second, the fossil record is spatially incomplete. And finally, if ecosystem dynamics are important to the biotic response, then it becomes increasingly tricky to actually know what to expect in terms of how ecosystems respond to particular stresses. But then, on the other hand, the hope is that if we can identify expected physiological responses to particular stresses and then combine that with the spatial information that we have, then maybe we will actually be able to zoom in on some particular stresses that seem most significant for these extinction events. Or maybe that none of them have explanatory power, and that's really useful too. So, okay, let me just end by touching on some of the major questions that I think would have a lot of significance if we could begin to address them to move this process forward. So we'd like to know how much magma freezes, how much magma erupts. Does the gas released at depth reach the atmosphere? How long do individual LIP eruptive episodes last? I think that's a really interesting question. And then what feedbacks apply? So we've talked basically about direct forcings, but what happens when you change climate for ocean circulation, for example? And then how different are different LIPs from one another in terms of their environmental consequences? And how will those different stresses shape the geologic record? And finally, this question that we started with, can LIPs cause mass extinctions? And if so, how? So I realize maybe it seems a little frustrating that I ended my talk with the same question that I started with. But remember that we don't actually have a great consensus on the cause for any mass extinction, right? So in that context, I actually think it's really exciting that we're getting closer to being able to understand not only whether large igneous provinces and mass extinctions have a causal link, but also how that causal link might operate. So that's it. Thanks. Question or two?
I'll try to get out 3 questions really quickly.
Sure.
You didn't mention NOx, but maybe that only applies to internal combustion engines. You didn't mention, this is not meant to be a criticism, I thought your talk was fantastic. You didn't mention the effect of sulfur dioxide on ozone depletion, and you didn't mention the presence of the Carboniferous coal beneath the Siberian traps, which might have greatly magnified those effects.
Yeah, thanks. So, with reference to sulfur dioxide, that is something, I didn't emphasize that, but that is something that's included when we do the simulations of ozone depletion. Sulfur dioxide, the sulfates can be important as nucleation surfaces for heterogeneous reactions that destroy ozone. So that is included. What was and what was the last question?
Carboniferous coal.
Okay. Oh, the coal, yeah. So the coal that's an interesting one, right? It's an idea that's out there that one of the sedimentary rocks that's present in the Siberian basin is coal, which contains a lot of carbon, and heating of that coal could lead to release of a lot of carbon into the atmosphere. So that's one of the ideas, I think, that maybe motivates Ying's work, right? When she assumes a particular carbon isotopic composition that's released into the atmosphere, that's sort of agnostic about the genesis of that carbon. It's just assuming a particular isotopic composition. So coal could well be consistent with that isotopic composition. The issue there is that it's tricky actually in the field to find evidence that a lot of that coal has been smelted, or ultimately the carbon in that coal has been released to the atmosphere. But it's an interesting idea, yeah. And then the NOx I don't think would be significant in the Permian. Other questions? Thank you. Thanks.